So now we've seen how to use high-order procedures, they're called. That's procedures that take procedural arguments and produce procedural values to help us clarify and abstract some otherwise complicated processes. I suppose what I'd like to do now is have a bit of fun with that and sort of a little practice as well. So let's play with this square root thing even more. Let's elaborate it and understand what's going on and make use of this kind of programming style. Well, one thing that's you might know is that there is a general method called Newton's method for the purpose of which is to find the roots, that's the zeros, of functions. So, for example, to find a y such that f of y equals 0, we start with some guess. This is Newton's method. And the guess we start with, we'll call y0. And then we will iterate the following expression. yn plus 1, this is sort of a difference equation, is yn minus f of yn over the derivative with respect to y of f evaluated at y equal yn. Very strange notation. I must say, ugh. Okay. The derivative of f with respect to y is a function. I'm having a little bit of unhappiness with that. But that's all right. Turns out the programming language world notation is much clearer. Now what is this? This is what we'll call Newton's method. It's a method for finding the roots of the function f. And it, of course, sometimes converges, and when it does so very fast. And sometimes it doesn't converge, and oh well, we have to do something else. But let's talk about square root by Newton's method. Well, that's rather interesting. Let's do exactly the same thing we did last time. A bit of wishful thinking. We will apply Newton's method, assuming we knew how to do it. And we don't know how to do it yet. Well, let's go. What do I have here? The square root of x. It's Newton's method applied to a procedure which will represent that function of y, which computes that function of y. Well, that procedure is that procedure of y which is the difference between x and the square of y. Indeed, if I had a value of y for which this was 0, then y would be the square root of x. See that? Okay. I'm going to start this out searching at 1. Again, completely arbitrary property of square roots that I can do that. Now, how am I going to compute Newton's method? Well, Newton's method, I have it right here. In fact, what I'm doing is looking for a fixed point of some procedure. This procedure involves some complicated expressions in terms of other complicated things. But I'm trying to find the fixed point of this. I want to find the values of y, for which if I put y in here, I get the same value out here, up to some degree of accuracy. Well, I already have a fixed point process around to do that. And so let's just define Newton's method over here. A procedure which computes a function and a guess, initial guess. Now, I'm going to have to do something here. I'm going to need the derivative of the function, I'm going to need a procedure which computes the derivative of the function computed by the given procedure f. I'm trying to be very careful about what I say. I don't want to mix up the word procedure and function. Function is a mathematical word. It says a mapping from values to other values, set of ordered pairs. Okay? But sometimes I will accidentally mix those up. Their procedures compute functions. So I'm going to define the derivative of f to be, by wishful thinking again, I don't know how I'm going to do it. Let's worry about that later. Of f. So if f is a procedure, which happens to be this one over here for a square root, okay, then df will be the derivative of it, which is also, well, the derivative of the function computed by that procedure. df will be a procedure that computes the derivative of the function computed by the procedure f. And then given that, I will just go for looking for a fixed point. What is the fixed point I'm looking for? It's the one for that procedure of one argument x, which I compute by subtracting x, that's the yn here. Okay. The quotient of f of x and df of x. Starting out with the original guess. That's all very simple. Now I have one part left that I haven't written. And I want you to see the process by which I write these things, because this is really true. I start out with some mathematical idea, perhaps. Okay. By wishful thinking, I assume that by some magic I can do something that I have a name for. I'm not going to worry about how I do it yet. Then I go walking down here and say, well, by some magic, I'm somehow going to figure out how to do that. But I'm going to write my program anyway. Wishful thinking, essential to good engineering. And certainly essential to good computer science. Okay, so anyway, how many of you wish that your computer ran faster? Yes. Well, but derivative isn't so bad either. Sort of like average damping. Derivative is a procedure that takes a procedure that computes a function as its argument. And it produces a procedure that computes a function which needs one argument x. But we all know this definition. It's f of x plus delta x minus f of x over delta x, right? For some small delta x. So that's the quotient of the difference of f of the sum of x and dx minus f by x divided by dx. I think the thing was lighting up correctly when I bounced the parentheses. Okay. Now I want you to look at this. Just look. I suppose I haven't told you what dx is. Somewhere in the world I'm going to have to write down something like that. I'm not interested. This is a procedure which takes a procedure and produces an approximation, a procedure that computes an approximation to the derivative of the function computed by the procedure given, by the standard methods that you all know and love. Now, it may not be the case that doing this operation is such a good way of approximating a derivative. The numerical analysts here should jump on me and say, don't do that. Computing derivatives produces noisy answers, which is true. Okay? However, this again is for the sake of understanding. Look what we've got. We've started out with what is apparently a mathematically complex thing. And in a few blackboards full, we've managed to decompose the problem of computing square roots by the way you were taught in your college calculus class, Newton's method, so that it can be understood. It's clear. Let's look at the structure of what it is we've got. Let's look at this slide. This is a diagram of the machine described by the program on the blackboard. There's a machine described here. And what have I got? Over here is the Newton's method function f that we have on the leftmost blackboard. Okay? It's a thing that takes an argument called y and puts out the difference between x and the square of y. Okay? Where x is some sort of free variable that comes in from the outside by some magic. Okay? So the square root routine picks up an x, and builds this procedure, which has the x rolled up in it by substitution. Now, this procedure in the cloud is fed in as the f, okay, into the Newton's method, which is here, this box. Okay. The f is fanned out. Part of it goes into something else, and the other part of it goes through a derivative process into something else to produce a procedure which computes the function which is the iteration function of Newton's method when we use the fixed point method. So this procedure, which contains in it by substitution, remember Newton's method over here, Newton's method builds this procedure, and Newton's method has in it defined f and df. So those are captured over here, f and df. Starting with this procedure, I can now feed this to the fixed point process with an initial guess coming out from the outside, from square root, to produce the square root of x. So what we've built is a very powerful engine which allows us to make nice things like this. Now I want to end this with basically an idea of Chris Strachey, one of the grandfathers of computer science. He's a logician who lived in the, I suppose about 10 years ago or 15 years ago he died. I don't remember exactly when. He was one of the inventors of something called denotational semantics. He was a great advocate of making procedures or functions first-class citizens in a programming language. Okay, so here's the rights and privileges of first-class citizens in a programming language. Allows you to make any abstraction you like if you have functions as first-class citizens. The first-class citizens must be able to be named by variables. And you're seeing me doing that all the time. Here's a nice variable which names a procedure which computes something. Okay? They have to be passed as arguments to procedures. Well, you've certainly seen that. We have to be able to return them as values from procedures. And I suppose we've seen that. We haven't yet seen anything about data structures. We will soon. But it's also the case that in order to have a first-class citizen in a programming language, the object has to be allowed to be part of a data structure. We're going to see that soon. So I just want to close with this and say having things like procedures as first-class data structures, first-class data, allows one to make powerful abstractions which encode general methods like Newton's method in a very clear way. Are there any questions? Yes?
Could you put deriv instead of df directly in fixed point?
Oh, sure. Yes, I could have put deriv of f right here. No question. Mm-hmm. Anytime you see something defined, you could put the thing that the definition is there. And you should get the same result. In fact, what that would look like, it's interesting.
Lambda. You could put the lambda expression in there.
I could also put deriv of f here. Okay? it would look interesting because it would be open paren, derivative of f, close paren on x. Now that would have the bad property of computing the derivative many times, because every time I would run this procedure, I would compute the derivative again. However, the two open parens here, both would be meaningful. I want you to understand syntactically that that's a sensible thing. Which if I were to rewrite this program, and I should do it right here just so you see, because that's a good question. Of f and guess to be fixed point of that procedure of one argument x which subtracts from x the quotient of f applied to x and the deriv of f applied to x. Guess. Okay? This is a perfectly legitimate program because what I have here, remember the evaluation rule. The evaluation rule is evaluate all of the parts of the combination, the operator and the operands. This is the operator of this combination. Evaluating this operator will, of course, produce the derivative of f.
Carry it one step further, you could put the lambda expression that's in
Oh,
here.
of course. Right. Anytime I take something which is defined, I could put the thing it's defined to be in the place where the thing defined is. I can't remember which is definiens and which is definiendum. When I'm trying to figure out how to give a lecture about this in a freshman class, I use such words and tell everybody it's fun to tell their friends. Okay, I think that's it.